welcome everyone to the webinar. I'm not the person setting up the IT here, so I don't know if you can say hello back yet, or if that comes later. But I'll have the Q&A window up and watching for questions and answers. But if you have the ability to just blurt them out, that would be fine as well. So this is a webinar today on how the challenges that Poland will face in building new nuclear power plants. I am Brian McDonald, Dr. Brian McDonald. I am a structural engineer, and I have in my career as a structural engineer, one of the things I've done is designs and design peer reviews for nuclear power plants. And what I'm doing now, as I'm getting closer to retirement, I have switched modes, and I am now developing standards, U.S. standards for nuclear power plants. And so I've been spending some time in Washington, D.C., trying to change and simplify and streamline the standards that we use in the U.S. for nuclear power plants, because basically in the design of new nuclear power plants, both large conventional plants as well as small modular reactors and micro reactors, there is a sense that the regulations are somewhat archaic now, and there are better ways to regulate these plants so that it's not so expensive, and we can do that without sacrificing any of the quality of the plant. So that's what I'm working on. If Poland is going to rely on any U.S. standards, you can blame me for the quality of those standards going forward. But lucky for you, I will not be the one presenting the content here. That will be my colleague Andy Kadek, who I feel honored, pleased to introduce here. It's easy for me because I worked with Andy for several years, so I know firsthand of his knowledge of the nuclear industry. I will be challenged to call him Dr. Kadek through this webinar because I know him as Andy. But Andy is a former president and CEO of Yankee Atomic Electric Company, and is a professor in nuclear engineering at MIT. Dr. Kadek's authored numerous papers on nuclear management, nuclear power, and advanced reactors, and he has served as president of the American Nuclear Society, contributing significantly to advances in the nuclear industry. So Andy is going to use all of that experience and identify today what he thinks are some of the challenges that Poland will see as they try to implement what is a pretty ambitious plan for nuclear power in Poland. So, you know, the experiences around the world have not been a series of unmitigated successes in building nuclear power plants. And Andy will provide some insights on how to use those experiences to avoid the same pitfalls. So, Andy, I see I've done it already. Dr. Kadek.
No worries, no worries.
Perhaps the best place to start is to ask you a question to set the stage here. Why are we bothering with this webinar? And by that I mean, why is nuclear power so important right now? Not just for Poland, but for the world.
Well, thank you very much for the introduction. I think pretty much the world is now beginning to realize we need additional electricity and energy. And nuclear power has its ups and downs. And the recognition, the fact that it is needed for many reasons. Obviously, climate change is one of the big ones. But certainly in Europe, energy security is very vital. And I think that's one of the main reasons that Poland is thinking going in this direction. You know, the Ukrainian situation is pretty bad. Nuclear has been selected because it's a 24/7 source of electricity. It doesn't vary as a function of the sun or the wind. And these plants, when they're built and operating, they can last from 60 to even 80 years now in the United States. Some plants have actually applied for license extensions up to 80 years. It's very true that the initial capital costs are extremely high, but think about that as an 80-year investment. And that's kind of one of the reasons why I'm sure Poland and other countries are looking at that.
Okay, so thank you, Andy. You've been involved in many recent nuclear power plant designs and the construction of those plants around the world. Given that experience, why should Poland be concerned with how nuclear power plants are currently designed and constructed?
Well, as you mentioned, the experience hasn't been terrific. Even countries that have a lot of nuclear experience, such as France and the US, they've suffered recently tremendous cost overruns. The average time for construction of a new plant has been 17 years, if you can believe it. The average cost overruns go from a factor of 2 to 4 above the initial cost estimates. China is the exception. They've built over 55 plants, and the reason they're being able to build them so fast and so well is because their infrastructure and their workforce is there. They roll from one plant to the next. So they've had the experience, whereas in the US and France and other countries, we haven't built many plants in the last few years. But in China, even they have cost overruns, and it really depends on the technology they choose. The Chinese technologies, they built a lot of Westinghouse plants, the AP1000s, which they modified. Their cost overruns are small, largely because of the experience base. But for the non-traditional plants like the EPRs, their cost overruns are a factor of 4 higher than what they originally estimated. But in any case, the other plant that has a good example is the United Arab Emirates. Now, this country is unique because it is a first-of-a-kind plant in a first-of-a-kind country relative to nuclear experience. They built 4 plants in 9 years. They hired a contractor from Korea, and they brought in their own labor. They used some of the local labor, but their average cost overruns for those 4 plants are about 1.6, which is actually quite good. Why are the results good for those types of plants like UAE and also the Chinese? They built an existing plant design. Poland is also doing the same. They hired an experienced contractor to manage the overall project, so there was clear accountability. The regulator, this is a very important point, was part of the solution and not the problem. In the United States, we feel, at least personally, sometimes the regulator is the problem, causing numerous delays that may not be necessary. The management oversight in the UAE was very strong. The government support was strong and, interestingly, and more importantly, consistent. And financing was not an issue in the UAE, as you might imagine.
Yeah, and Andy, I'll just I was involved in the design and construction of that plant, and I just want to second what you said. It was very important there that the Korean contractors were building a plant, the same type of plant that they had just built in Korea. Now, of course, there were some changes because cooling water, the water input's different and whatnot, soil's different, seismic design's different. But they laid all that out ahead of time, working with the regulators to make sure that everyone was satisfied with the changes. Now, it didn't happen without any problems, but they were able to respond quickly. And I think in terms of nuclear build out in general, that is one of the success stories.
Right.
But there are plenty of stories that went the other way. So, given the challenges the world has been experiencing, Andy, for all sorts of reasons, building out new nuclear power plant and new nuclear power plant designs, do you think, given Poland's ambitious nuclear power plans, do you think they'll face some of these same challenges?
Well, quite clearly, let me see if the next slide gives you some background on Poland's plans, but they do have an established national nuclear power program, which lays out their broad goals for the nuclear program. They also have an active atomic law, which provides sort of the guidance relative to regulatory and safety standards. And they, in fact, established a regulator, excuse me, called the National Atomic Energy Agency. They're like our Nuclear Regulatory Commission. But most of their experience in this agency was dealing with isotopes in a small research reactor. So they're going to have to modify their regulations to accommodate large nuclear power plants. But what right now, at least the plan is for Poland, they want to build 3 AP1000s, Westinghouse designs. These are huge plants, 1,250 megawatts. They're pressurized water reactors. They've already chosen a site, and I cannot pronounce the Polish pronunciations, otherwise I will be kind of laughed out of the room. But they also have a company that they've retained or created to manage the project, this PEJ. They're also proposing 2 advanced Korean reactors that were built in the UAE and also in Korea, the 1,400 megawatts. And they're planning to look at least 24 small modular reactors of the boiling water reactor type built by General Electric, only 300 megawatts. So it's a very ambitious nuclear program. Now, relative to some of the challenges, this slide, it's kind of busy, but imagine going into a construction program with roughly 4 million documents to review in terms of systems you have to engineer, design, number of drawings that have to be modified, and reviews of vendor qualifications and specifications. It's a huge task. That's why they call these projects mega projects. And right now, I'm not exactly sure Poland is ready to do it on that scale, which is why it's very important to hire an experienced contractor that has the capability to do all of this stuff. And especially when they do subcontracting, they're going to have a lot of subcontractors providing subcomponents, individual pumps and valves and so on and so forth that have to be procured, reviewed, and tested.
So, Andy, we build large, complex structures all over the world pretty successfully, I think, in Poland and elsewhere. Why is nuclear so different? Why does it seem to be so difficult?
I think the simple answer to your question is it's highly regulated and it's overseen by many, many different agencies. But the most significant agency is the Nuclear Regulatory Commission. They have very stringent demands for quality assurance, documentation. Just to give you an example, to use a particular pipe, you have to be able to show that the material specifications for that pipe and trace it back to the original smelting or forging that pipe was created from. And that documentation is very important, very expensive, and you have to test every component to a point where they assure that the function will be proper. And it's a monumental documentation task. But we have some lessons to be learned from past experiences. And these lessons basically are to establish a secure success path. And financing is very important, because if you're arguing about who is going to pay what and in what order, you're going to end up with a stalled project. You need to hire experienced new nuclear plant construction people. And what I say by new nuclear plant, you can't rely on people who built a plant 20 years ago and think that same process is going to be workable. Clearly, cost and schedule are very important, and monitoring that, hiring of qualified contractors without a doubt, and subcontractors. There's a famous phrase about being able to budget realistically, not optimistically. Most people, when they budget, do budget optimistically, and that is the cause for a lot of pain. The regulatory policy is very important. The UAE model is good. The UAE people adopted pretty much the US Nuclear Regulatory Commission standards, but they modified them to make them more flexible in terms of being able to quickly resolve any differences. And this is, I would believe it's one of the most important parts of the oversight of nuclear power, a reasonable regulator. And my view basically is to oversee cost and schedule, you need to basically have not just paper reports, but a field presence for people who will be on site and able to actually see progress and not rely on a report. But again, also creating an experienced oversight organization. Let me see if I can find a slide that perhaps I want to include about the, it's not in this one, but maybe another one. Brian, you might have it about lessons learned from past successes. Well, maybe I'll go down a little bit more. Okay, this one.
Yeah, so just to interrupt, in the Q&A, we're hearing that everyone is seeing what I'm seeing, Andy, is still the first slide of the deck in.
Oh, you're not seeing the slides. Oh,
we're not seeing the slides. So maybe I could try from here, or we could just keep going in with question and answer mode. So.
Oh gosh, I'm sorry. I didn't realize that. How could that be?
I thought it was on my end, but maybe not. So which slide number would you like up, Andy?
Well, let me go back down here. Let's see if I can get it back up. Hold on a minute. I would say slide number 13.
Success is possible?
No, lessons learned from past projects.
Okay, I got it. Slide, the 13th slide, but oh, there it comes. I can see it now, Andy.
You can see my slide?
It's still in edit mode, but I can see the slide, so I won't try sharing. I'll let you continue.
Can you see it now, non-edit mode?
No, it's still in edit mode.
But you can see the slide.
Yes.
Okay. Well, there are lessons learned from past projects, which is, I think the most important lesson is they started construction without a complete detailed engineering design. And this is important. You know, Poland's going to build an AP1000, which has a standard design, but some of it will need to be modified based on current site conditions. And without allowing the incorporation of local and national construction standards, you're going to have difficulties in being able to meet these schedules, which means detailed design suitable for construction. Then you have lack of regulatory clarity or experience. What are the detailed requirements? Those need to be laid out early. And especially now with Poland trying to develop a regulatory process for nuclear power plants, they need to, I would say, synchronize all of their regulatory bodies that affect the construction of a nuclear power plant. In doing some reviews, I saw that Poland has numerous regulatory agencies in environment and if you will, transmission, distribution, all of the electrical systems needed, and they need to be synchronized and consolidated into a complete set that the builder can design to once they agree to the concept of AP1000, for example. There is also poor selection of contractors, and many of them are not qualified for nuclear grade work. As I mentioned earlier, there's very stringent training requirements, quality control requirements, independent oversight requirements that some local small contractors just simply don't have. The challenge is managing through a project management organization all these multiple contractors. The integrated schedules are very complex. Putting all these pieces together, as you saw in the earlier chart, about the number of documents, number of vendors required. So integrating all that into a master plan is going to be very, very important. The other thing that typically happens is you have a failure to recognize, and I use the word admit, problems early. and you'll say, oh, we can make it up a little bit later. We'll try to squeeze it in over here. No, address the problem right away, because it will make it worse if you don't. Again, we mentioned the regulatory inflexibility. They need to be constructive. Inadequate qualified work. It's going to be a problem because, not many people are building nuclear plants in Europe, and finding the nuclear qualified workers in welding and electrical and concrete and structures is going to be important. In the US, we are very litigious. Hopefully that's not the case in Europe, and vocal opposition can create issues. Now, if you go to the next slide, perhaps, since you're going to be showing them.
I think you're still showing, but I can
Okay.
I can try.
Okay, if I'm showing, good.
It's still on that lessons learned from past project slide.
Okay.
It seems like when you share your screen, it shows whatever's on your screen immediately when you do that, and then it never changes again after that.
Oh.
So my apologies to the viewers, but like I said, Murphy's Law, it all worked great last night, and now of course when we're live, things happen.
Okay, so what slide do you see now?
Lessons learned from past projects is what I
Okay,
said.
how do I don't know how to fix it.
Well, I can share from here, but before I do that, I'd like to emphasize a couple of things that Andy has said, because it's so clearly true from my experience. So one of the things that's happening in the U.S. and is in Poland's plan are the new small modular reactors, a very exciting development in nuclear power. And I've been talking with, I can't name names, but I've been talking to some of the designers that are developing these. And their chief concern for implementing these in the US is the costs of doing nuclear construction in the US because of regulatory requirements that aren't there. If I'm going to design a critical care hospital in California in a seismic zone, the cost of designing a nuclear power plant in Texas, which is essentially seismic zone 0, is an order of magnitude higher, even though the structures and the systems perhaps are no more complex in the end. And that's because the regulations for it are higher here. So just to put out a couple numbers, for small modular reactors, the current designs in the US, the cost for those, about 60% of the cost are the actual concrete and steel structures that house the equipment. So more than half the cost is sort of the civil construction. And because of the nuclear regulations in the US, the price of building those structures for a nuclear plant is 5 times what it would be for a hospital or for a police station or other critical facilities. And that's what we're working on now, is trying to lessen that gap. When we in the US tried to build a new nuclear power plant in Texas, and I worked on that as one of the designers. And sorry, Andy, I'll spend a little bit more time on this, but there was a little piece of that nuclear power plant called the ultimate heat sink. It was essentially a concrete box full of water. And it was my job to QA the seismic design of that. And the designer sent me the design calculations. It was 60,000 pages, probably more than a high rise in San Francisco along a fault, for the seismic design of a concrete box. And to jump to the sad end of that story, we did achieve an operating license and a construction license. It cost almost $1 billion before the first shovel hit the ground. And now the financing and the financiers have pulled back, and it's not clear that that new plant will ever get built because of the regulations. The other thing that Andy said that was really important is, even if you have a standard plant and you want to use a cookie cutter design and design the standard plant in 3 different sites, there's always site specific changes you have to make. So the plant in the UAE, United Arab Emirates, the Barakah nuclear power plant, I think was a successful design build of a plant. But they were building the same type of plant that they built in Korea, relocating it to the United Arab Emirates. I mentioned this before, but there was two sort of big changes for the design. One is that the cooling water was coming in at a much higher temperature in the Gulf than in Korea. That's no surprise. So the intake structures all had to be enlarged. All the cooling piping had to be enlarged. That was you know, it might not seem like a big deal, but that took an inordinate amount of time compared to the implementing the rest of the design. The other thing was seismic, and for structural design, seismic is going to control everything. You know, you'll have to design for wind and for, you know, missiles carried by the wind hitting the structures and that sort of thing. But seismic kind of rules, and in the United Arab Emirates, it was being built on deep sand and other softer soils, whereas the plant that they were mimicking, the plant in Korea, was built on a rock site. So all of the seismic calculations and design needed to be redone. So I just wanted to mention my personal experiences as being right in line with what Dr. Kadek was discussing. So,
but that's a good point. The Polish site they've chosen for the first plant is on the coast, but the access to water for cooling is far away, and it's going through some sort of an endangered area of dunes. And how they're going to transverse that as direct cooling system is going to be complicated. This is where the other regulatory bodies come in and approvals need to be made. So it's, as I said, do not underestimate the challenge and do not believe everything your contractor who's proposing to build this plant says. We had an expression by President Reagan, trust and verify. That's a very good philosophy. Now, I don't know what slide you can see now, but
Andy, let me try to share. I'm still seeing a different slide, but let me see. I'll put up the success path for Poland. Can people see that?
Yeah, we did that one already.
Okay. You would this slide?
Got that. Yeah.
Okay. Tell me.
I'm looking at slide number 10, I believe. Yes, 10. Yes.
Okay.
Now this one I think is important for the big picture. Where do you stand in the construction process? And you should be able to adjust. And I was recommending, and I do recommend, 2 independent groups of experienced engineers and constructors, in addition to your normal QA functions and groups, on site with key offices of the major contractors to monitor their work. And I call it a construction review board. They do this monthly, provide reports and assessments of progress and status. Then a senior construction oversight board, which would be overall project oversight of senior utility people who may not be hands-on people at the site, but would be able to say, from a big picture, this is what I see going on here, and this is where you're missing the boat, and this is where you need to make some adjustments. I think with those 2 additions, you might be able to get some independent corroboration of what the vendors are telling you about progress.
Excellent. And I will. I was thinking we do questions and answers at the end, but I want to. There's one comment that came up in the Q&A that is so applicable to what we're doing here in the U.S. It sounds like maybe it's a universal principle. And Andy, I'll put it to you very quickly. But I'm going to try the name, Andy. I don't mind being laughed at, but Kozma Chutowski, I'll say, says, I think a major obstacle may be the technical background of the administrative staff, and also the level of scientists' involvement in decision-making process is simply inefficient. And he has some other things. You're welcome to read in the Q&A. But I think those are the important points. And I'll let you respond, Andy. But I'll say amen to that in the U.S. And this is one of the things I've been doing this year. I'll be going to Washington, D.C. next week to talk to the decision makers, the administrators, the regulators. We're trying to get more technical input, and it's very difficult. It's too apropos to today. It's two sets of people speaking different languages most of the time, even though it sounds like English from afar.
I think you're right. The technical background of the regulatory staff needs to be greatly improved, as is the scientific input is helpful, but in this area, I think what we really need is experienced construction people who know how to put something together and make sure that in fact it's done properly. I think that's the key. And from an administrative staff, the vendor, the contractor will hopefully be able to provide qualified leadership. And what I mean by that is, don't just say, okay, because I worked on this project, I'm qualified to do this work. Every project is a different challenge, and these people need to be good leaders to be able to make people work together and not fight each other, because there's a lot of competition among contractors typically. You don't want to do it my way, and I'm going to do it my way regardless. That doesn't work. All that does is cause conflict, and it's not productive. So you've got to have a leadership team and a management team that sort of is able to bring these people together in a way that they work together constructively, because you'll have a lot of different professional opinions, and those professional opinions need to be decided by a group or one person who's totally in charge. So that's a piece of advice.
Yeah, thanks, Andy. And maybe that's a good segue into, I was going to ask you if you had some particular things you wanted to caution the polls about what this daunting plan they have for nuclear power. And if you'd like, I can share the slide.
Yeah, put that up, please. Yeah.
Cautions. Okay. But go ahead.
Well, the biggest caution I think is being able to decide, are you really serious about lessons learned? I gave a presentation at the Structural Failures Conference in Poland last spring, and the title of my talk is Past Lessons Learned, and I highlight the not followed part. And that's the problem. That they study all these lessons and they ignore them because they think they can do better. I won't make these same mistakes. The other caution is, you're going to spend billions of dollars, and the billions in this case could be for maybe 5, if not more, billion per plant. And that's a lot of money, and where that all going to come from is yet to be determined, I understand. The caution is, don't deny reality. There will be problems, as in any big project. The longer you wait, the worse the cost will be. Training of a workforce is essential, because in the United States, we had a number of utilities who were very familiar with building and operating coal and oil and natural gas plants. Different standards. And these standards need to be sort of inbred in the nuclear workforce. And you need to train your staff to that point. Establish the safety culture, because everything is very important. Small mistakes matter in a nuclear power plant. And as I said earlier, make the regulator part of the solution. Work constructively with the regulator. And when you develop your regulatory system, be sure it does have that flexibility to solve a problem, not ask 1,000 questions and then delay the project.
Thanks, Andy. And we're getting pretty close. We scheduled 40 minutes for us jabbering and 5 minutes to answer some of your good questions. I see a couple of good questions in already. So maybe Andy, I'll just jump to our last slide here and set it up with a question to you. This has all been pretty doom and gloom, I think, from us so far, reading between the lines. Do you really think Poland can be successful pulling off this ambitious
Well,
nuclear
I
project?
do. I do. This presentation is just an eye opener. It's not meant that Poland is going to fail. It really hopefully will open the eyes to what you need to worry about when you embark on a big project like this. And the clarity in leadership, clarity in regulations, and accountability. And it's really important that the Polish government apparently is going to be financing a lot of this. They have people qualified on staff to assure that these things happen. I mentioned the sound financial structure. The worst thing that happens is when the politicians get involved. Then everything starts slowing down and getting complicated. People think about, well, what's the political risk of doing this particular thing or not? That will set the project back quite a bit. High quality expectations and have a plan B. So if things don't work the way you originally planned it in your schedule, have workarounds ready to go in the event that plan A doesn't necessarily work. I believe Poland can do this. This plant AP1000 has been built in China, has been built in the United States, and I think in other countries as well. But it's a doable proposition, but it's going to require an eyes open strategy.
Thank you, Andy. That's a good spot to end. We have a couple of questions. The first question is my favorite, and thank you for whoever put it in by making it anonymous, so I don't have to try to pronounce another name. But it's two questions. One is, we've mainly discussed large traditional nuclear plants in Europe, but what about SMRs, small modular reactors in fusion? And it says, I've noticed significant investments in these technologies in the US, and you mentioned them earlier as well. Do you think Poland could benefit from adopting these technologies in the future? Before you answer, Andy, I will give my short answer is yes. And I'm very excited about them here as a structural engineer, because the containment and the passive safety functions make the structural design so much easier. And there should be an associated streamlining of the regulations that we're working on now. We don't need huge containment structures for these. The containment's within the mechanical assembly itself. But in any case, I've said too much. This is a question for Andy.
Well, SMRs are a very important part of the future mix. When I was at MIT, my favorite SMR was a high temperature pebble bed reactor. Okay, it's not on Poland's list. Everybody in SMR world wants to be the second one to build one. And that's generally true for all these new technologies. There are probably 50 or so new small reactor designs worldwide being developed. I noticed the Polish government is interested in the BWRX 300, which is General Electric's 300 megawatt small modular reactor. It is being proposed for Canada and Estonia, as far as I know, and Poland, and maybe other European countries. I think Canada is now in the lead for that. I think they will be fine because they work best on distributed generation. They're going to be slightly more expensive than the large, economies of scale type plant. But if built and they can be replicated, we're looking at economies of not scale, but economies of production to reduce the cost of these plants. So my guess is you build one and you could probably build the next one for maybe 2/3 of the price, the next one probably for half the price. And that's the kind of the progression of cost as it goes down. So I think I'm a believer in SMRs. SMRs are good for data centers, even smaller SMRs, 10 megawatts, even smaller, 20 megawatts, 30 megawatts. For data centers, for example, they could be very useful in those cases. But yeah, SMRs could be a big role player.
Yeah, in the US, there's early talk right now to try to solve this first of a kind technology, which is so expensive. So we have, like Andy said, there are different SMR designs out there that are competing against each other. And there's actually talk of, with government help, um, aiding one of those to get the first one up and going, so that all the burden isn't on one of the developers to foot the bill for the first of a kind, really expensive first plant. That they'll actually get some help doing that, and then like Andy said, the second of a kind, third of a kind, be much less risky and much less expensive. The other thing, in addition to the small nuclear reactors, I mean, it's modular reactors and the fusion reactors, there's also something called micro reactors. And there is a lawsuit right now, speaking of regulators and attorneys and other decision makers in the US, to be by a couple of developers of micro reactors to say that the Nuclear Regulatory Commission rules, those regulations do not apply. These are not like the old nuclear power plants. These are more like nuclear material you would be storing for medical purposes. And there's really the risk of loss of containment is so small in relation to large nuclear reactors that those don't try to apply NRC regulations to us. We can do these per the building code essentially. So it'll be interesting to see where that lawsuit ends up. So the second question, Andy, another good question, touched on potential solutions for Poland to avoid the challenges faced by the UK. That said, do you think Europe should invest more in nuclear research, particularly in university-led research reactors, to strengthen its capability in the nuclear field? Now, I will preface Dr. Kadek's answer by saying you're asking an MIT professor whether you should do more university research. So this might be asking a hammer if nails are a good idea. So oh, he's going to get a prop, I think.
Got a dog barking. I apologize.
Oh.
Research from a university perspective is essential. And let me tell you why, besides the obvious. You need qualified engineers and scientists to be able to support a nuclear industry. And you can't grow a nuclear engineer. He's got to be trained. He's got to understand the physics, or even a civil or a structural engineer. All those people in the university level are essential in bringing into practice a workforce that's capable of understanding the safety, understanding the risks of operations, for example. So I'm a very keen supporter of nuclear research and development. When originally the Department of Energy in the United States started embarking upon this program that Brian mentioned relative to let's help the innovators to build out these nuclear plants. Bill Magwood at that time was head of a DOE, Department of Energy, and he did a lot to support research at universities. And one of the key questions was, as Brian mentioned, how do we get this started with the amount of money required to actually build one of these things? And I told him, I said, you know, if you want commercial participation, you got to do an 80-20 deal. 80% of the government support and then 20% of the private sector, because you can't do it any other way, because no commercial entity will risk, you know, $1 billion, which so many have already, to start a reactor that may not be licensed, for example. So you need government support. You need university researchers to be able to help and innovate in some of these new designs. And I'm 100% behind that. And Poland, I understand, is expanding its nuclear programs at several universities, which is essential.
Thank you, or thank you, Dr. Kadick. But there's another question that came up. I'm not going to try to answer this one as a structural engineer. I have no idea how to answer this one, but maybe this is something you know, Andy. But the question is, how long will it take to deplete identified uranium sources? How long will these reactors run into the future before we're out of uranium?
There are wonderful studies about that, and the time, just uranium-235 from a mining perspective, people are estimating 200 years, okay? Very roughly. But depending upon how much you want to pay, you can extract uranium from seawater. So it's I would say an abundant supply. The question is price. And what people are now looking at or have looked at in the past is what we call these breeder reactors, where we in fact use non-fissile uranium-238 to make uranium-235 and uranium-233 and plutonium, so that we can in fact use what is now a waste from the commercial mining industry. And if you design the reactor properly, the reason they're called breeders, because they make more fuel than they consume. Breeder. So eventually, I think when the price of uranium gets to be too high, which it is not now, you'll be transitioning to breeder reactors, which are liquid metal cooled like sodium. And these breeder reactors will have an infinite supply of fuel for operation.
And I'm old enough to remember every 10 years, people saying we'll be out of oil in 10 years. So
That's right.
I'm guessing other sources of uranium are probably out there and not identified yet, but I don't know, but
Exactly.
I wouldn't be surprised.
You're right.
I think we're 3 minutes over.
No, sorry.
I'll check the Q&A again and see.
Well, I apologize for the slide confusion, but hopefully you got the message.
Yeah. One more is, and this is an interesting one. So we'll take one more minute, and that has to do with nuclear waste, a very controversial subject here in the U.S. But how the nuclear waste management can deal with it easily to solve this energy crisis and improve the economy. So I don't know if you have a nice concise answer about nuclear waste. I don't want to say anything because I'll get myself in trouble.
A concise answer is, technologically, it's easy to do. Politically, extremely hard to do. For those of you who followed this issue, you will know that we had a nuclear waste deep geological site in Nevada at Yucca Mountain. It was going great. Testing was done, scientific analysis was done, a license application was submitted. Then the politicians got involved and killed the project. So in Europe, you have many small countries. My recommendation for Europe is you get together and you figure out where would be a good place for all of Europe to dispose of its spent fuel. And in the future, we may be recycling spent fuel. France recycles its used fuel and produces volumetrically a much lower quantity for disposal. But progress is being made. In the U.S., unfortunately, not so good. In France,
my concise answer is that this is a very important issue for politicians, because it's something they can use to scare people. But for people that actually understand nuclear waste and what their actual hazards are and the tools that we have available, I think the technical world is not nearly as concerned as the political world about nuclear waste.
that is so true.
We still have some questions coming. Andy, I've got time to go. And
I'll stay on, sure.
Yeah, if people want to stay on, stay on. If not, thank you for joining. What made this a very interesting webinar is the good questions we're getting. So I thank the participants for those. And we'll try to get through these last couple very quickly. Andy, what are the precautions and also challenges for small reactors? How the nuclear waste management can be dealt with? So again, small reactors and the relation of small reactors to nuclear waste management.
I don't
make
think
it easier or harder?
I don't think there's much of a difference. If you use conventional reactor technology, like light water reactors, the problem is essentially the same. It's limited small quantities of highly radioactive material that have to be kept out of the environment. Most places will be geological disposal. Some countries are looking at long-term storage, but from a small modular reactor to a large reactor, it's just the quantities of stuff that have to be disposed of.
All right, another one popped up, Andy, or Dr. Kadick, and I'm gonna read this one to you because this is a fantastic opportunity for you to make enemies all over the world. So
Yes.
Here's the question. If you compare nuclear technologies from the US, South Korea, and France, what are the pros and cons? Which I think to me, which is your favorite?
That's a hard and an easy question. I think the Korean technology is solid. It's mostly based on US Westinghouse pressurized water reactor technology, as is the French. The French in their advanced reactors, the European pressurized water reactor called EPR, I think they overdid it relative to having core catchers in, double containments, things like that. They made the plant so expensive that it's probably going to deter people buying them. But the government felt that that's what they needed to satisfy public opinion. The US, I think, is a good, reliable design. We'll see how the Vogtle plant, which is the US AP1000 plant, performs. I think it's based on 50 or more years of experience. So I think the Koreans and the US have probably got the right equation to try to balance cost versus safety. The French, I think, have overdone it a bit because they're too high on the cost.
I don't think you made too many enemies with that.
Okay.
That response. So, good job. I think that gets us through all of the. Oh no, here's one more. How long do you think it'll wait for? How we will wait for fusion reactors? And I will answer this one, Andy. That I'm old enough now. This is like the running out of oil question. It's always 20 years into the future, and it's always been 20 years into the future.
That is the right answer, except the number is now 35.
Okay, so you're not looking to fusion reactors right around the corner.
No, even if they're able to demonstrate more energy in than out, if you look at the energy density, in other words, per square foot, how much power, how much area do you need to get usable energy out of a fusion device? You'll find that it's huge because the fusion machines are also very big, but the amount of stuff you need to support the fusion reaction in terms of power and so forth is large. So I think it's not a scientific problem, it's an engineering problem. And that's harder to solve.
Okay.
We can make fusion.
Very good.
Remember what we're going to do with fusion. We're going to boil water.
Yeah.
1,000,000 degrees centigrade to boil water. That somehow doesn't compute to me.
Well, it'll be great when it comes. I'll say
That's
that
correct.
for it. It's the promise of fusion energy production is
Right.
fantastic. Yeah, and there's a note saying the fusion. I think what you're saying, Andy, the fusion reaction already works thorium to uranium-233. I don't know enough about thorium and uranium-233 to have any opinion on that. But.
The thorium is another fuel that can be used, but again, it's like uranium-238. It's a breeding substance that you need to put thorium in a reactor to have it breed uranium-233, which is fissionable, and that's another challenge in the cycle.
What do you think about thorium reactors in general as a technology?
I think they're fine, but what people miss is it's a reprocessing cycle, and you need to refuel it with uranium-233. So you need to take the used fuel out, reprocess it, and put uranium-233 back. But even though thorium is available around the world, it still requires some kind of fissile material to run.
Okay. That's the advantage of having an MIT professor on the call. I
Occasionally.
could hardly spell thorium if someone asked me to.
Yeah.
I just know it needs a building to house it, and
Big
if the
building,
building needs steel reinforcement. That's where I come in.
and seismically qualified.
That's right. Okay, I think we've hit all of the questions, and again, thank you to the participants. You're who make or break these webinars, and the questions were very good. So appreciate it, and I think that brings us to an end.
Thank you.